Let's continue our learning about lines and planes by looking even closer at lines and planes. Remember our work with lines from before? So we have talked about lines in two-space, so two-dimensional lines. We have talked about putting them in the vector form where our slope is equal to AB, so that's like our direction vector. Parametric equations where we break it up into pieces, and we've looked at expressing it just as the x and just as the y, or in this combined form, and of course defining our parameter as well. T is an element of the real. And then we've talked about our scalar equation here, where our normal vector AB is given by the values of A and B in our Cartesian or scalar equation. Then we extended to three space, which is all basically the same idea. We just have that extra z term added in, so position plus parameter times direction vector, where direction vector is given by ABC. We've looked at our parametric equation, where I can give these each separately as my x component, y component, and z component, or all combined here. And t is an element of the real. And we talked about why we cannot have a scalar Cartesian equation in three space for a line, because it's defined in terms of a line being perpendicular to it. So if we defined our vector n, we saw that there is actually an infinite number of lines perpendicular to it as this one rotates about. And so rather than defining a line, it defines our plane pi. All right. And then we started learning about planes. So what have we learned about planes so far? Planes exist in three space. So, I mean, when we're working with two dimensions, we are working within a plane, but we don't need to define it. Just it's a two-dimensional space we're all working in. Now we're talking about planes existing in three space. And so we have like our XY plane, YZ plane, ZX plane, and so on. So we got multiple flat surfaces here interacting with each other in three-dimensional space. We have talked about finding a vector equation. Remember, a vector equation, not the vector equation. There's different ways of representing this, where we define this in terms of our position and two direction vectors, and we define both of our parameters. Or in our we have our parametric. So once again, we can have our separate x, y, and z components, or put it all together in a single representation like this. So x component, position plus first parameter, or a value times first parameter, d value times second parameter. So those are the pieces from my position vectors, and y and z. And of course, remember to define both parameters. S and t are elements of the real. And then finally, our scalar Cartesian equation, ax plus by plus cz plus d equals 0, where our ABC defines our normal vector. And remember, sorry about that. Remember, this is a plane, not a line in three space, which we just discussed, and this is a unique representation. All right, let's move on and let's learn something new. In our first question here, we are asked to find the parametric equations of the plane that passes through a given point, so 1, negative 3, 2, and is parallel to the xy plane. So let's highlight our important pieces of information here to keep track of. We're finding parametric equations of a plane, not a line. We know it passes through a point, a given point, and it's parallel to the xy plane. First thing we're going to need to do, or first thing we're going to do, is find our vector equation. And let's actually make a little description here, or a little diagram that represents what we're looking at, just to help us visualize before we get into our step calculations. So we will draw our x, y, z axes. X, y, z. We know that the plane passes through the point 1, negative 3, and 2. So x is 1, y is negative 3, and z is 2. So we have this point up to, so it's going to go through that point right there, and it's parallel to the xy plane. So from a side view, this is my xy plane, this is my z-axis going through. If it's parallel to my xy plane, it's going to kind of be hovering above it like that. So that's our two-dimensional view. Let's sketch that in our three-dimensional view here. So it's going to contain this point right here, and it's basically floating above our XY plane because it's parallel to it. And remember, parallel just means it's never going to intersect. And it's parallel to our XY plane, so let's just kind of indicate that at least here. So parallel to the plane running between X and Y. And I want to be clear that my red plane here is on top. So I'll just recolor that a little bit. All right, and so we can kind of see there's a gap here between our planes. All right, and we're going to be talking about something being perpendicular or parallel or whatever in reference to our axes. And how do we represent our axes in vector form? Well, we just use our unit vectors. So I'm going to label them on here as well. So my vector I, and my vector j, and my vector k. Let's zoom in a little bit, make our life a little easier. I, j, k, and I know k only has a magnitude of 1, but if I make that arrow any shorter, you won't be able to see it very well. So remember, I is a vector in the direction of the positive x-axis with a magnitude of 1. So I is equal to 1, 0, 0. And j is a unit vector that goes along our y-axis, so 0, 1, 0. And k represents our z-axis, 0, 0, 1. All right, cool. We have a bit of a diagram, a little bit of setup and foundation to help us with this question. Let's keep going. What are our steps? First thing I'm going to do is I'm going to find the vector equation of this plane. So step 1, find the vector equation. And remember, to do that, I need 1 point and 2 direction or basis vectors. And do I know 2 non-collinear vectors that describe this plane? Yeah, if I look at the diagram I just made, the xy plane is going to be, well, it has 2 vectors that lie in it. It has the I vector and the j vector. Like, they're literally part of the axes that define the plane. So they definitely lie in the plane, and we already know just from definition that they're orthogonal, 90 degrees to each other. That means they're definitely not collinear, so we can use them to define our plane. So let's go ahead and do that. Plane is defined in this vector equation. Position vector, or point on the line, or on the plane, sorry, 1, -3, 2, plus t, or so let's use s, times my first direction vector, which I'll use I, 1, 0, 0, plus t times my j, 0, 1, 0. And don't forget to define our parameters. S and t are elements of the real. All right, looks pretty good to me so far. Next, we're going to convert to parametric. So vector equation to my parametric equations. So I'm going to have x, actually, oops, wrong spot. X, y, z. X is equal to 1 plus s minus, or plus 0t, so I don't need to write it. Y equals -3 plus 0s plus 1t. And z is equal to 2 plus 0s plus 0t. So z equals 2. And let's also define our parameter here before we move on and forget. S and t are elements of the real. And what do you notice? S can be any real value. So x can be like any real value plus 1. So basically any real value. And my y component, t, can be any real value -3. So like I can reach any real value I want, which means I can have any possible value I want for x and y as long as z equals 2. So here we just have the scalar equation of our plane. And we could rearrange it if we wanted to, like the ax, whatever. So basically our equation is 0x plus 0y plus 1z minus 2 equals 0. Or, I mean, that's just equivalent to z equals 2. So what that means is we can reach any xy value we want as long as the z value is 0. And we could kind of see that already from our situation up here. I can go any direction I want in the X, Y, Z direction. There's no restriction. There's nowhere I can't reach, as long as my height, so to speak, my Z, has a value of 2. So it's identical to the XY plane, just shifted up 2 in the Z direction. And so just as an example, we can reach points like 1, -3, and 2, or 0, 0, 2, or -9, 47, and 2, or 1,000, -0.5, 2. Like any possible real value we want for X and Y are fine. For our second question, we can repeat this with the XZ plane. This one is on the practice sheet, so I will leave that for you to try on your own. On this next page, we have a series of practice questions which I'm going to show you, but not work through right now. If we're doing this live, you can share your answers in the chat. If you're just watching this as a pre-recorded video, you can just pause and look at the screen and answer these questions on your own. If you have specific questions about how to answer these, or you need us to work through it together, just shoot me a message. That's something we can do. But for the sake of time and this just being a lecture and not also a series of practice questions repeated over and over, I am going to skip this. But if you are in my class right now, this is something that we can work on and I can answer questions about together. Anyway, moving on. Let's do a little bit of review and collection of knowledge. Let's answer some of these questions together. First of all, what are all the ways that two lines can intersect in 2 space, or R2? So what are all the ways two lines can intersect in 2 space, or we can also think of it as what are the different numbers of solutions we can have to our system of linear equations. Once again, just like you did at the start of grade 10, we can have a unique solution. So there is one point of intersection. We can have no solution, where the lines are parallel and distinct. Oops, and distinct. Or we can have infinite solutions, where the lines are coincident and lying on top of each other. All right, what about in 3 space? So let's talk about the same thing, but in 3 dimensions. Well, once again, we can have a unique solution. We can have lines which are parallel and distinct. A new possibility that we have to consider now is skew lines. And skew lines are 2 lines that are not parallel, but there's no intersection. And the lines in this, these are called skew lines. These can only exist in R3. They cannot exist in R2. So in R2, anytime we have any 2 lines that are not parallel, if we extend them far enough, eventually they'll intersect somewhere. But in 3-dimensional space, let's see if we can sketch this in an appropriate manner. So X, Y, Z. Maybe I have some line here. And somewhere below it, I have this line here. And they're just never going to meet the point of closest approach. Might be like somewhere like here. And if from a top-down view, we would see one goes this way, one goes this way. But they're not actually meeting because they're in 3 dimensions. So we have our gap here. So that's going to be skew lines. I'm just going to write a simpler version of this picture in the space to keep things tidy. So our skew lines are not parallel, but do not intersect. And no intersection means no solution to that system of equations. So it's zero solution, no solution. And finally, we can have coincident lines once again in R3, where we have an infinite number of solutions. Coincident, infinite solutions to our system. So lines will intersect at a single point, or no points if they're parallel and distinct, or skew lines, or if they're coincident, infinitely many points. More things to think about. What are all the ways that two planes can intersect in 3 space? What are all the ways that 3 planes can intersect in 3 space? What are all the ways that a line and a plane can intersect in 3 space? You can pause for a moment and think about this, or use props to help you. So if you want to use a piece of paper or multiple pieces of paper and a pencil to represent your line, what are the different ways we could try to fit things together and think about how they would intersect? And I'm going to go through this briefly and slightly out of order. If we think about a line and a plane, how many ways can they intersect? There are going to be 3 ways. First, the line intersects the plane at exactly 1 point. Second, the line does not intersect the plane and it's parallel to the plane and there is no point of intersection, so no solution. Or the line lies on the plane. In this case, there are infinite solutions. So we can see the first one given here. So we're going to have 1 solution. So it intersects. We can have 0 solutions, or a plane is like chilling down here, and our line is somewhere above in parallel, and we've seen examples of that already in previous questions, I believe. Or we can have infinite number of solutions where the line lies in the plane. So I got my plane hanging out and the line runs directly within that plane. When dealing with 2 planes, there's going to be 3 ways they can intersect. It can be along a line. So, for instance, we have our first plane here. Oh, that looks terrible. Let's try that again. Plane 1, and then plane 2 goes right across it. And let's zoom in a little bit, and we'll move that over a little bit. All right, that's our first case. Second case, I have 2 parallel planes. So they're going to kind of float above each other, or however we want to think to rotate them, and they do not intersect. Remember, anytime we see parallel, just kind of means they're not going to intersect. So we can think of them having the same direction vectors, just like 2 lines having the same slope. And we can have coincident planes. So just like our coincident lines, they're going to lie within the same space, right? Like on top of and like through each other. So plane 1, oops, I don't like that. Let's tidy that up. Plane 1, and then plane 2 is in like the exact same space. Finally, our intersection of 3 planes. I'm going to switch apps here just because I do not have enough room to draw that on the other slide. So we can have a situation like with our x, y, and z coordinates, where I'm going to have something like this. So all them are meeting there. So I'm going to have plane 1 and plane 2 and plane 3, and they all intersect at a single point P. So case 1, they're intersecting at point P. Intersect at point P. Case 2A, is we're going to have our 3 planes intersecting along a single line. So I'm going to have my line intersect at line L. And let's sketch our planes. So plane 1 and plane 2. And plane 3. And looking at this, I kind of think of it like a book that's open, or like back cover, front cover, and pages inside, and they all meet at the spine. So if that's helpful, you can think of it that way. We're going to have case 2b, where L is the intersection of 2 coincident planes and a third plane not parallel to the coincident plane. So we're going to intersect at line L, but 2 planes are coincident, and plane 3 is not parallel to the coincident planes, is not parallel to plane 1 and 2, which are coincident. So let's take a look at that. So I'm going to have my line L. We'll have our plane 3 just hanging out here. And my plane 1 and 2. So plane 1 and plane 2 is right on top of it, coincident. So once again, we can kind of think like a book. We got our cover, we got our first and second pages open, lying flat, and then we have a third chunk of pages, and that's like our plane 3. So once again, if the book metaphor helps you, I find it very helpful. I wonder if I can move that over. And we're going to have case 3, where the plane of intersection of 3 coincident planes is the plane itself. Or in other words, all our planes are kind of lying coincident to each other. So I'm going to have plane 1, plane 2, and plane 3, and they intersect at an infinite number of points because they're all lying like on top of and within each other. And once again, if we want to think about our book metaphor, plane 1 is folded all the way open. Plane 2 is also folded all the way open. And plane 3 is also folded all the way open. So it's like a stacked layer, but it's not, I mean, like in a physical reality, we think of it being on top of each other, but actually they're all melded and smushed into the same thing. So they're all occupying the same coordinates, the same physical position, so to speak, if we were talking about the real world. All right, so those are, and let's label this. So planes are coincident. So I can't zoom out to show you the whole note all at once, but you can take a look and you can pause the video and copy this down however you want into your notes. Now that we've discussed the various ways that lines and planes can intersect, let's do some calculations and see how do we actually find these things mathematically. In our first example, we are asked to find the intersection of the line r equals 1, -6, 5 plus t 232 with the plane 4x minus 2y plus z minus 19 equals 0. So the first thing we're going to do is we're going to take the vector form of our line. So for a line, we're going to go from vector form of our equation to parametric. So let's take a look at each of those components. For the x component, x is going to be equal to 1 plus 2t, and of course, as we've seen previously, just grabbing these values from here, y is equal to -6 plus 3t, and z is equal to 5. Sorry, there's a typo in the question. This should be -5. So this is a -5 plus 2t. All right, cool. Now what we're going to do is substitution. So we're going to sub our values in. Values into the equation of our plane. So let's do that now. So step 1, step 2, so 4. Instead of x, I know that x is equal to 1 plus 2t. Minus 2 instead of y, I know that y is equal to negative 6 plus 3t plus z. Instead of z, I know z is equal to negative 5 plus 2t minus 19 equals 0. Let's do our distributive property and then collect our like terms. 4 plus 8t plus 12 minus 6t. Be careful distributing that negative here. Make sure you have the correct signs, positive or negative, on your numbers. Plus negative 5 plus 2t minus 19. Now we're going to collect our like terms. I know you know how to do this, but I'll still highlight our like terms just to make our life a little bit easier. All right, so I'm going to have 4 plus 12 is 16, minus 5 is 11, minus 19 is going to give me negative 8. And 8t minus 6t is 2t, plus 2t is 4t. So we're going to see that 4t equals 8, or in other words, t equals 2. And this is where we get the intersection. So let's just label that. This is where we get intersection. So this is where both our plane equation and our line equation are true. So this is a value that exists on both. So it is a point in the line and the plane. So it is a point where the plane and the line intersect. So let's actually find our conclusion. What is the location of that actual point? So in our step 2, we solved for t. In step 3, we're going to use t to find our actual x, y, z point. So step 3, looking at our parametric equations, plugging in our value for t. So t is a value of 2. So we're going to have an x value of 5 at our point of intersection, and y, negative 6 plus 3 times 2 is going to be 0. And our z value, negative 5 plus 2 times 2 is going to be negative 1. So therefore, our point of intersection is at 5, 0, negative 1. And that wasn't too bad. These are all pieces of knowledge and calculation we've done before. We're just putting them together in a new way to solve something new. So, step 4, state conclusion. And just for flavor, we'll add a quick little diagram here. What did this look like? So I have my plane. I have a single point of intersection. My line L goes through. And this point P right here is at 5, 0, and negative 1. Let's take a look at a second example. Let's try this again in our second example. Here we are asked to find the intersection of the line x equals 2t, y equals 1 minus t, z equals negative 4 plus t with the plane x plus 4y plus 2z minus 4 equals 0. Step 1, as before, is to put our line from vector form into parametric form. It's already in parametric form here, so we don't really need to do step 1. It's all ready to go. So I'm just going to write out those values. X equals 2t, y equals 1 minus t, z equals negative 4 plus t. We're going to sub our values in for step 2. So we have our scalar or Cartesian equation of our plane. Let's plug in our values. Instead of x, I'm going to put 2t. Instead of y, I'm going to put 1 minus t. Instead of z, I'm going to put negative 4 plus t. And minus 4 equals 0. Once again, we're going to expand. collect our like terms, and solve for t. So 2t plus 4 minus 4t minus 8 plus 2t minus 4 equals 0. I'm going to label my like terms to make my life a little easier. 2t minus 4t is negative 2t, plus 2t is going to give me 0t. That's interesting. My numbers, so I'm going to have 4 minus 8 is negative 4, minus 4 is negative 8. Minus 8 equals 0, so 0t equals 8. How is that possible? 0 times what number gives us 8? Nothing. There is no answer. If we rearrange and solve for t equals 8 divided by 0, that's not defined, so this is not possible. Impossible. So what does that tell us? How come we've reached a point where this is impossible? That's because we're doing the calculation to find the point of intersection between our line and our plane, and if there's no real value that allows that to be true, that means there is no point of intersection. So this means, therefore, there is no solution. So in our concluding statement, we can say, step 4, therefore, there is no intersection between the line and the plane. And how is that possible? We've talked about this case already, but let's sketch it quickly. This is my plane, and my line is going to be parallel to it, above or below it, or however you want to think about it, such that they are never going to intersect. And that was one of the possibilities we talked about earlier when describing the different possible ways planes and lines can intersect with each other. And finally, let's try a third example. Here we are asked to find the intersection of the line x equals negative 4 plus 3t, y equals 0, z equals t, with the plane x minus 2y minus 3z plus 4 equals 0. And we're going to follow our same steps once again. Notice right away that our equation of our line is given in parametric form, so that's one less thing to worry about. I'm still going to rewrite it. We don't have to actually convert at all. We are not given in vector form to begin with. Z equals t. All right, step 2, we're going to sub into the equation of our plane. So x is negative 4 plus 3t minus 2y is 0 minus 3z is t plus 4 equals 0. Let's expand, collect our like terms, and solve for t. So I'm going to have negative 4 plus 3t minus 0, so I'm not going to write that, minus 3t plus 4 equals 0. This is looking interesting. Collecting our like terms, 3t minus 3t is 0t, and negative 4 plus 4 is 0. So we're going to have 0t equals 0. This kind of looks like what we had before, but we can actually solve this if we need to. What does this mean? Well, 0 times anything is 0, that's fine. T is 0 times 0. Basically, we can have, oh, that's not really helpful, but we can have any possible value for t we want. If we had 0 times 100, that equals 0. That satisfied the equation. If we had 0 times negative 2,000, that equals 0. So any real value will satisfy this equation. So that's great. What does that mean? It means all real values of t are possible. So this right here, this is true for all values of t, which means there's an infinite number of solutions, and that's one of the things we know to watch out for already. Visually, what does this mean? It means that if I have my plane, it means my line is going to lie in that plane. Or let's actually write our conclusion. Therefore, we have infinite intersections. In other words, the line lies in, oops, missed a word there. The line lies in the plane. All right, cool. So we've worked through 3 different examples and examined our 3 different possible modes of intersection between a line and a plane. Back to the intersection of lines, and let's learn a little bit of new vocabulary here. If a linear system of equations has no solutions, so if they are parallel in R2, well, R2 or R3, or if they are skew lines in R3, then the system is said to be inconsistent. So no solutions means inconsistent. If a linear system has at least one solution, it is said to be consistent. So inconsistent means no solutions. Consistent means at least one solution. And let's take a look at some calculations here. Determine, well, without calculations. We'll work through it though. Determine without calculation the number of solutions to each of the following systems of equations in R2. Let's see how we're going to go about doing that. And remember, no solutions, and we're just in R2. So the only test I really need to do is to see if my lines are parallel or not. So we're just dealing with flat, 2-dimensional R2 space surface. So parallel means no solution. Any line that is not parallel will eventually intersect, and so there will be at least one solution. So let's take a look at our 2 different lines given here in question A. And let's figure out, how do I tell if they're going to be parallel? Well, let's take a look at our direction vectors, or we don't even need our actual direction vectors. We can just use our normal vectors. My normal vector for line 1 is going to be equal to a comma b, so 2 comma 5. And my normal vector for line 2 is going to be 3 comma 4. And if these lines are parallel, then their normal vectors must also be parallel, because they're offset by the same amount. They're offset by 90 degrees. So if these 2 are parallel, these 2 will be parallel. So I don't need to convert them or anything. I can work directly with my normal vectors here. That's fine. And I want to know, is n1 a scalar multiple of n2? And let's actually do it. We can probably see right away, but let's do our test. So I'm going to have 3 over 2 equal to 4 over 5. Are those equal? No. We can see right away that they are not equal. So therefore, these are not parallel. So this is not true. So we see that the lines are not parallel because their normal vectors are not scalar multiples of each other, which would also tell us that their direction vectors are not scalar multiples of each other. If they are not parallel, they will intersect at least once. So therefore, there is one solution. They will intersect at a single point. So technically we did some calculations here, but the idea is that we didn't calculate to find what the point of interest is, or the point of intersection is, if it exists. We just did some quick calculations in terms of, are these lines parallel, and answered indirectly that way. Let's take a look at our next example. I have 2 lines, 3x minus 2y plus 8 and 9x minus 6y plus 20 equals 0. Same as before, I'm going to start by looking at my direction vectors. So for my line 1, my direction vector is going to be 3, negative 2, or my normal vector, sorry. And for my second line, my normal vector is going to be 9, negative 6. And you can probably see right away already that these are going to be scalar multiples of each other, but let's go through and actually confirm. N1 equals k, N2 we need to confirm. So 9 over 3 is equal to negative 6 over 2, and we can see those both equal negative 3. So we can see right away that N2 is equal to 3 times N1. Therefore, these lines are parallel. and will not intersect. Well, actually, we don't know that yet. Sorry, we know they're parallel, so that means they're going in the same direction. So they're either they're not going to intersect, or they are coincident, and they are going to intersect everywhere. So we're going to have to do a test to figure out which case we're dealing with here. So let's just label this. So our options, so parallel and distinct. Oops, I guess they're both parallel. So I should just use the word distinct as our one case here, or coincident. And we just set up here that the scalar multiple between these two is going to be, actually I made a small error here. Forgot my negative sign there, and so +3, and I think everything else is fine already. So we've already seen that the normals are scalar multiples of each other. That means the direction vectors will also be scalar multiples of each other. So the lines are, the direction vectors are scalar multiples, but we haven't proven if the positions are the same scalar multiple of each other. So we're going to go back to our equation, and we're going to look at these values right here. And if line A and line B are multiple, or line 1 and line 2 are scalar multiples of each other, then these will also have to have the same scalar multiple value of k. So let's take a look. So we're going to take a look at our values. Here I did my n2 value over my n1 value, so my value from line 2 over my value from line 1. So I'm going to do the same thing here. 20 divided by 8. And what do we notice here? This does not equal 3. Therefore, these lines are not coincident. Because if they were, that value would be the same as the value we had before, because there's no solution that allows this to be true. So therefore, the lines are parallel, and there is no solution. So this option is out the window. This is the option that we have in this situation. Let's add one final label before we move on. We said previously, if a linear system has no solutions, it's said to be inconsistent. We have no solutions here, so this is inconsistent. If it has at least one solution, then it is consistent. So let's just keep those terms in mind as we keep working. And we've talked about 2-space. Let's talk about 3-space. Let's determine the number of solutions for the following lines in R3. Here we're going to have line 1 in vector form, 1, 2, -1 plus t, 4 minus 1 minus 3, and line 2, 2, -2, 7, plus our parameter times 1, 0, -5. How are we going to solve this? Well, last time we compared our normal vectors, because that's what we had easy access to dealing with our scalar Cartesian form of our equations. Here I have the direction vectors, so I'm going to work with those directly. So in order to compare the direction of these lines, I'm going to compare my direction vectors. So it's right off to the side here what we're going to do. We're going to, step 1, compare my direction vectors. So let's do that here. My direction vector for line 1 is 4, -1 and -3. And my direction vector for line 2 is going to be 1, 0, -5. And let's see if they are scalar multiples of each other. So m1 equals k, m2, 4 over 1 equals -1 over 0. It's -3 over -5. We can see pretty quickly that those are not the same values. These are not equal. So they are not scalar multiples. And therefore, these are not parallel. So m1, actually don't need to rewrite that, is not equal. So these are not parallel. But we're still left with the remaining question. So not parallel, but do they intersect at one point? Or are they skew? Because remember, we're dealing with R3, three-dimensional space, so you know, there's more options. So just because they're not parallel does not mean they're going to intersect somewhere. So think about how we can determine that. And I'm going to pause here for a moment. I recommend you pause and try to answer the rest of the question before I continue on and show you how to do it. All right, so since these lines are not parallel to each other, this indicates that these lines either intersect exactly once or they are skew. If the lines intersect, there must be a single point that is on both lines. So to follow along with this idea, we're going to convert both of these. So let's go ahead and do that. So I'm going to convert each of my lines from vector form to parametric form. And as I do that, I'm just going to make a slight change so we don't get confused about what value goes with which line. And I'm going to, change my parameter here, t, into an s, because it's just a variable. It doesn't matter what we call it. Well, now let's try this. So for L1, my parameters are going to be x is equal to 1 plus 4s, y is equal to 2 minus s, z is equal to negative 1 minus 3s, and for L2, my parameters are going to be x. Our parametric components are going to be x is equal to 2 plus 1t, y is equal to negative 2 plus 0t, so I don't need to write that, and z is equal to 7 minus 5t. So our step 2 was to go from vector to parametric form. Our next step is we're going to use substitution or elimination to solve for s and t. We're going to use 2 of our parametric equations. So let's label our step here. Step 3, I'm going to choose 2 equations and solve for s and t. So I'm assuming my x's are equal, so I'm going to have 1 plus 4s equals 2 plus t. That'll be my equation 1. And my equation 2 is 2 minus s equals negative 2. We can tidy those up a little bit. And as I rearrange, I'm going to find that 4s minus t equals 1. And 2 plus 2 is 4. Minus s, 4 equals s, or s is equal to 4. And so we've actually solved for s already. That was convenient, so let's just kind of highlight that. We're going to come back to that. And now we can solve for my t value using substitution. So I'm going to take equation 2 and plug it into equation 1. So 4 times 4 minus t equals 1. 16 minus t equals 1. 16 minus 1 is 15 equals t. So I know my s and my t value, and this is just like the questions I've done before where I've solved my parameters, plugged them in, and seen if our final value is going to work as well. So let's go ahead and try that out. So I'm going to sub s and t back into my parametric equations and see if I get the same value output as a result. So step 4, we're going to sub s and t into our parametric equations. So let's do that here. I'm running out of room here, but we'll be okay. So L1 and L2. Let's plug our values in. X is equal to 1 plus 4 times 4 is 17. Y equals 2 minus s, so minus 4 is negative 2. Z equals negative 1 minus 3 times 4. Negative 1 minus 12 is negative 13. For L2, x equals 2 plus t, which is 15, which is 17. That's the same as in L1. That's encouraging. Y equals negative 2. Same. That looks encouraging. And z equals 7 minus 5 times 15. And we're going to get a value of negative 68. So we didn't quite make it. It looked like we were going to have a point, the same point existing on both lines, but not quite. So our values are inconsistent. And therefore, what did the question actually ask us? Find the number of solutions. Therefore, no solutions, no intersection between L1 and L2. And I'm going to leave it at that. I'm not going to answer B. If you like, you can pause here and work through that on your own as a separate exercise for yourself.